Okay, good. So I hope you have enjoyed the discovery of this magical ability for pandas to be able to map and apply map onto different parts of the data frame and to perform this magical goal of programmable content transformation. Okay, so if you're excited as me now, let's just join me and hop over to the Spider lab. All right, so run your Spider and let's begin our experiment with creating a data frame. Now here I'm going to also show you another way to create data frame. Um, Earlier on, we have been creating data frames based on list of lists. And the inner list is always a row, interpreted as a row by the pd.dataframe. Right? So what we're going to do here is to need a df6. And along the same way, I can also illustrate how we can create a new data frame using dictionary. So notice there's a curly bracket here. All right, so this is a dictionary keyed by the letters A, B, C, and D. And then the column values here, while I type horizontally necessarily because it's programmed, actually it's going to be thought of, interpreted by PD data frame as a column. So it's going to be column A with a label A and having values 111, 2223. 3. Okay, good. So similarly, we have BCD, and then those are the column values. So when we do it this way, we don't have to specify columns equals to what, because all the information is there. So when we run this, we will be able to get a very decent data frame, right? So let's experiment with what we have earlier on, and I'll just do it in the runtime space here. So SS6B, right, as shown in our slide, was to extract the column B from df6. That's true. And then we can look at SS6 map, the result of applying a map function, right, to SS6 underscore B. And the map function is just having a lambda, taking in a scalar value x, and then performing 10 minus x onto it. And the outcome is that we will get the complement, the tens complement, right, of the original series SS6 underscore B. Good. Now let's take a look at how we may perform and apply. All right, apply. So we're going to have a df. What is df3 here? What is df3 here? df3 is a df3 is, oh well, we have to apply. Well, let's just apply to our df6 here. Okay, I need a df3. So let's just define a df3. Like I said, it's an experimental lab. So, nope, df3 is, okay, we can have ABCD as well. So let's just copy and paste from above. But we will have 8, 9. Okay, 3190, 3190, and 97. Great. Okay, so we're done. And we will now perform the apply transformation. We would like to return the percentage. Okay, what is the percentage of 8 with respect to this column? So it will take, we will be taking a column vector, and it is the whole column vector, the entire series, divided by the sum total of that vector. So we're performing one operation. All right, not a lot of operation. One operation of the series divided by the total sum by a constant. So when we do this, what is going to happen? What we get is df3 itself, but converted to its percentage weightage in its own column. All right, in its own column. Now, what happens if we do the same thing? All right, but now we say it's row property. Right, so we apply, and we like the row weightage. Then what we do is we just simply say x is equal to 1. Okay, and then we print df3 row property. Now you might say, but then we actually call it column vector. Should we change it to row vector? Now actually it doesn't matter. If we just call it vector, VEC, that would do. Although I agree with you, right? When we call it column vector and we apply an axis equals to 1, it probably might indicate to other readers that something somewhere is wrong, isn't it? It's like you copy and paste it and it's not the right thing. So it might be safer if you are trying to apply it to potentially row and column safely, because mathematically it's sound, then you just call it a vector or a series. That's fine, because it doesn't matter whether it's column or vector or row. But if you do indeed to mean it to be a row vector, because column vector doesn't make sense, then make sure you call it correctly row vector. The naming of the variable is very important, and it serves as a sort of a automatic implicit documentation, and it helps a lot, both to other programming teammates and your future self, right? Because next time you read it, you're not going to understand what it says. So here correctly, it's going to add up row-wise to 100% because all the numbers are converted to its own percentage weightage in its row, not column. All right. And finally, we can also think about applying the lambda across everywhere, right? That is where we have our df everything ApplyMap. So df3 ApplyMap of a lambda that takes an element and multiplies it by 2. Yep, that's correct. Okay, and then we print df3 ApplyMap. So what this does is, why not? Has no attribute apply may, apply may. So apply map. I did say this is an experimental lab, so explosions do happen from time to time like that. So yeah, we get to see this magical wonder just multiplied by 2 everywhere, right? Just regardless of whether it's row or column. It's not structure aware, it's just element wise. So these two powerful functions, apply and apply map, they are very, very useful in terms of various things like cleaning up data, adjusting data, standardizing data based on the norm, the average, the median, the max minus min, the range, converting data to percentage weightage like we have done, and so on. So really, really wonderful, and saves us a lot of sort of, I won't say nightmare, but additional time to understand what's going on with all the for loops there. Is this for loop meant for programmatic control, or actually various different attempts? Let me try first time, second time, third time, right? Or is it really just a loop over the cells, and so on? So this really gives us two advantages at the same time. It does the right thing. It makes, because it condenses out that very logic and transformation expression here right in the lambda. It makes it very explicit, very easy to change. But number two is that it brings the data frame to the forefront. We are emphasizing that we are making changes to the data frame rather than saying we're having a for loop here, right? So those are the advantages. Now, also we talked about using apply and apply map using named function, right? So the usual define, I think I have there, and I can speed up by just copying and pasting. Okay, so let's do that. Where am I? All right, here. So I've just defined my map to be looking at um, this quartile. M is the row vec dot max. So row vec is the input row vector. Now, I'm emphasizing row vector because I'm saying to myself, I'm documenting it, that when you apply, better make sure you have axis equals to 1 to be in sync. If you ignore axis equals to 1 or you put axis equals to 0, it is column data, column series that will be sent to a what is meant as row vector. Something will be wrong, right? So it's a self-check, and we should use it consistently. So then we find the maximum, and our return vector is going to be our current row vector casted to a floating type. Casted means make a copy of it, but it will be copied as a float. Force convert every element to a float. Now, why do we need to do that? Because every element is so far an integer, and if you do that, something may break or something may not work correctly. So we're going to return a vector that is by default floating type. Floating type. So that's as big and as large as the row vector that was sent to us. So we don't have to check the size or whatever. And then we convert that to float. Okay. Then we enumerate, and that means we step through every single cell in sequence. The cell position 0 has this value. Cell position 1 has this value, and so on. So we enumerate through the row vector. If the value is the same as its own maximum, and we'll replace our internally generated vector, the floating point vector, with Q3 because it's a floating point number. So we'll replace that. But if it is not equal to the maximum, that means it's less than that, then we ignore and move on to the next loop. So in other words, we're scanning through the row vector if it's the maximum, which must exist, right? So at that point, we're going to replace it with Q3. And we may have to look through everything because there may be several values having the same max, like in this case 8399, right? So both nines need to be replaced. So then we finally finish up the loop and we return the modified vector. So return vector. So what we do then is to apply to df3 with my function using axis equals to 1. Yeah. And let's run it. Okay. So what do we see? So not surprisingly, we see that as we scan through row-wise, why row-wise? Because axis equals to 1, and that row is sent into my map, which finds the maximum value, calculates the quantile, and loop through every cell. If the 8 is equal to 9, no. 3 equals to 9, no. And 9 is equal to 9, so replace with the quantile 6.75 and the same. And then return that vector, which dot apply replaces its original value and then returns to df3 underscore mean column. And we also see that the dot apply with np mean across the row. How come it's across the row? Because of the axis equals to 1 will shrink, right? Will collapse the dimension because the input to np mean is a series, but the output is a single scalar average value. So that would reduce the dimension of the returned result, right? And if we check what is the type of the returned result of dot apply, that's series. But if we check the return type of the previous dot apply, everything is the same. So we have a function provided, we have axis equals to 1. We have a function provided, we have axis equals to 1. But because my map returns a vector and np.mean, which is also a function, a named function, returns a scalar, the type of the resultant object that dot apply returns is also different. Yep. So just be very sure, as I emphasized earlier on in the classroom, just be very sure of what you're doing before you run dot apply, right? So join me in the next